So what if we wanted to graph this function? Is the writing big enough for y'all to see that? I need to zoom in a little bit on that. I don't know why I was writing small tonight. But look, that's a fourth degree function. We've not seen anything like that really, right? So let's say we wanted to graph this equation, and we wanted to graph it pretty accurately. Well, one thing I can do, what's the graph going to be doing on the ends of the graph? What's its end behavior going to be? Is it up, up, down, 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 up, or up, down? Did y'all not write down your little chart? It's up, up, I agree, because it's even degree, fourth degree. That means it's either both up or both down. That highest degree term itself is positive, so that means it's up on both ends. But like I said right before break, that tells us nothing about what's going on in the middle of the graph, right? Like, where does it cross the x-axis, or does it even cross the x-axis? Where does it hit the y-axis? How many sort of humps and dips does it have, and all that kind of stuff, right? What if, oh, and the other problem is, do you agree? Well, first of all, we should know what the y-intercept is. Where is it going to hit the y-axis? 12, I agree. The constant term's always the y-intercept. But to find where it's going to hit the x-axis, this is what's tricky, and this is a lot of what's going on in chapter 3, or a lot of what we're going to be doing, is figuring out where does this thing hit the x-axis. If you knew all the x-intercepts, you know the end behavior, you know where it hits the y-axis. If you knew everywhere it hit the x-axis, that would probably give us a pretty good idea how to sketch the graph. So the problem with finding the x-intercepts here, remember, with those quadratic functions, we've got a way to find the x-intercepts. We can factor it. And whatever makes each factor 0, those are the solutions to that equation equals 0. Those are the x-intercepts. Even if we couldn't factor it, we saw an example where we could use the quadratic formula if we had to, and at least approximate where it hits the x-axis. The problem here is, first, I don't know how to factor this. Your math teacher is probably not supposed to admit that he doesn't know how to factor something, but I don't. I don't know how to factor this. In fact, I don't think anybody knows how to factor this. And we don't have a quadratic formula for the fourth degree, for a fourth degree equation, right? Technically, there is one, by the way. Technically, there is a formula that will find all the solutions of a third degree equation, and there's a formula that will find all the solutions to any fourth degree equation. You can think of them as sort of third degree and fourth degree analogs to the quadratic formula that we use to solve second degree equations. The problem is those formulas are very, very difficult. They're very complicated. I doubt that there's more than a handful of mathematicians in the world who could just sit down and use those formulas off the top of their head to find solutions to this. And even if they could, it would take a ton of computing, arithmetic to do it. So let's just say, for our purposes, there is no version of the quadratic formula that's going to help us. We don't know how to factor it. So we're going to learn how to find these x-intercepts. Maybe we'll get to a little bit of that tonight. We'll see. At least maybe scratch the surface. But what if we could factor this? So first of all, trust me when I say we're going to come up with a method we can use to find the x-intercepts. So if we could find the x-intercepts, well, then let's just pretend like we can factor this. We can't, but let's say we could. I think if I were to factor this, I would get this. So I believe if I were to factor this thing, this is what I would get. Now, I don't know how to get from, y'all look, I don't know how to get from here to here, okay? Like obviously I'm somehow cheating because I don't know how to get from here to here. But this is what I would get if I did. So this can be factored, and this is how it would factor. Let's say just hypothetically that we could figure out how to get from here where it's not factored to here where it is. Do you agree that if I could get it factored like this, I would know the x-intercepts right away? Like, what are the x-intercepts for this function? That's right. -2, -1, +2, +3. Remember, anything that makes a factor 0 is going to make the entire thing 0. And anything that makes the entire thing 0 is an x-intercept. Everybody see that? So -2 + 2 is 0. Then -2 is an x-intercept. -1 + 1 is 0. Then -1 is an x-intercept. 2 - 2 is 0. So 2 is an x-intercept. 3 - 3 is 0, then 3 is an x-intercept. Technically, y'all look, I'm crossing through x-intercepts. I'm going to say that those are the zeros of that function. They are the values of x that make this entire function equal to 0. But with that said, the zeros of the function are the x-intercepts of the graph of the function, right? The values of x that you could plug into this thing that make y equal to 0, those values are called the zeros of the function. The zeros of the function, well, if those are the values of x that make y 0, then those must be the x-intercepts for the graph of the function. Everybody see that? So the term zeros and the term x-intercepts are kind of interchangeable. The reason they're only kind of interchangeable is, remember that quadratic one we looked at after Celine's question where we used the quadratic formula and we found that not the one where they were irrational numbers that we could approximate, but the one where we used the quadratic formula and we got the two non-real numbers as the only things that made it 0. Well, those were zeros of the function. They were the values of x that made it 0, but they weren't x-intercepts because they weren't real numbers. Everybody see that? So a lot of times you'll hear people use the term zeros of the function and x-intercepts interchangeably. They are interchangeable, except you might have zeros that are non-real numbers, and those wouldn't be x-intercepts. But these are all real number zeros, so these are the x-intercepts of the graph. And so now I think I could do a reasonable job trying to graph this thing. You know, scale-wise, it might not be exactly right or whatever, but I think I could get in the ballpark of what this graph looks like. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 is the y-intercept, so that's there. The zeros, the x-intercepts are, the x-intercepts are -2, -1, 2, and 3. And we know that the end behavior is it's going up on each end, right? Essentially now all I've got to do is connect the dots to draw a reasonable graph. So y'all watch, because I'm about to do this and see what I'm doing. So I know that I start going up, I'm going up on the left, but I know I have to come down and hit that point because that's an x-intercept. It's on the graph. But I know I've got to turn around in time to hit that point because that's an x-intercept on the graph. And I know that I'm going to have to come up and hit this point because that's the y-intercept. And I know I've got to turn in time to come down and hit this point because that's an x-intercept. And I know that I've got to turn in time to hit that point because that's an x-intercept. And I know that I finish going up, right? So I've got this kind of W-shaped graph. Everybody see that? Now, a couple of things. First of all, remember, I have trivialize the process of finding these x-intercepts because, again, just remember, when I don't know how to go from this version of that function to this factored version. That's something we're going to have to learn to do. That's where we've got to do some math to learn how to do that. But once you're able to do that, once you have your x-intercepts, you can figure out the end behavior, you can figure out the y-intercepts. That's generally enough to draw a reasonably, a reasonable graph. Now, here's what we can't do with algebra. And you don't have to worry about, oh, this is going to be something hard to learn. You won't have to worry about this unless you plan to take calculus. This point is a relative minimum. Everybody see that? And somewhere up here is a relative maximum. And down here is a relative minimum. Algebra can't tell you how to find those points. Now, with a second degree equation, it can because it's the vertex. But in general, we won't know what those points are. In other words, this thing might actually come through here and it might go way down before it turns and comes back up. And this thing might come up and hit this y-intercept and it may not turn real quick. It might be going real steep and go way up before it turns to come back down. Y'all see what I'm saying? Like, we won't be able to figure that out with algebra. To find the relative maxima and these relative minima, you actually need calculus to do that. So that's kind of beyond the scope of what we're doing. But y'all look at this basic graph up on both ends, kind of a W. Like how low this goes, for example, you don't. You don't. But you do know this. If these are your two x-intercepts, you know that when you come through this one, somewhere you got to turn in time to hit that one, right? So in other words, look, you know that you're not going to do something like this where it just goes down forever because now you're too far and you've missed that x-intercept. You see what I'm saying? But yeah, you won't know exactly. But let me go to Wolfram real quick. We'll look at this one. We don't really have time to look at all these, but let's take a look at just this function, just so you can see that what we've done is, a reasonable picture of the graph. Like the main features will be accurate. So we got f of x equal x to the fourth minus 2x to the third minus 7x squared plus 8x plus 12. Let's get it to graph that for us. Let me see if I've typed it in right first. X to the fourth minus 2x to the third minus 7x squared plus 8x plus 12. Let's get it to graph it for us. There's our W. Notice it's up on both ends. Notice it's crossing the x-axis at -2 and at -1. You can kind of tell this is 10, so you can tell it's crossing the y-axis at 12. It has to turn in time. It comes back and hits the x-axis at 2. It turns in time to go up and hit the x-axis again at 3, and it finishes going up. That's basically what we did, right? And so that's kind of the rough idea of how we do this thing. Oops. I think that graph's not going to show up on the recording, just FYI, because I forgot to switch over to that screen. So my bad, but you get the idea. So for those of you who watched the video, just know that the graph we saw on Wolfram Alpha was pretty much like the one we sketched. Okay, so let's look at another example. But again, remember the trick is this kind of mysterious, I don't know how to factor that, right? And so, but I'm going to look at one more example before we begin to look at that, because there is one thing here. I wish I hadn't gooped this graph up so much. There is one thing here that we didn't take into account. Maybe I'll just use a fresh sheet of paper and do that real quick. So one thing we did not take into account when we graphed the thing. Let me see if I can just real quickly. Let's say I just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so there's my y-intercept. And -1, 2, 3, +1, 2, 3. And so then our x-intercepts were -2, -1, 2, and 3, and we were going up on both ends. Now what I did is, y'all look, follow my finger. I came down and hit this x-intercept, and I went through the graph and came up and hit this x-intercept and went through the graph and came up and hit this y-intercept and turned and came down and hit this x-intercept, went through the x-axis, came up and hit that x-intercept, went through the x-axis, finished going up. We know we got to go up on both ends. But there are other ways that I could have done that that still would be smooth, continuous curves. For example, what if I'd done this? When I got to this x-intercept, maybe instead of going right through the x-axis, maybe it just hits that point and turns and goes back up. It could do that because maybe then what it does is comes down and hits this point, turns again and comes down and hits this point. That's possible, but if that did happen, then I know I would have to turn now and go up because I got to hit that y-intercept, and I know I've got to do this and come down and hit that x-intercept. But maybe here, how do I know that I go through the x-axis and then turn and hit that and go through the x-axis? Maybe I do the same thing again. Maybe I hit it and turn and hit it and turn like that. That's a different way to draw that graph that still has the correct end behavior, that's still a smooth continuous curve, and still has all the correct x-intercepts and the correct y-intercept. Y'all see that? So that's the other little feature we got to figure out, is each time the graph hits one of the x-intercepts, does it turn, like bounce off and, like in this case, go back up, or does it pass right through the x-axis? And so there's actually a way to figure that out too. Now notice in our particular graph, it went through the x-axis each time, right? It didn't turn and go back up on any of them. It went right through the x-axis. Okay, let's take a look at this one. We're going to do a similar thing with it that we did with the last one. So this is 5th degree. Do y'all agree that the end behavior should be down on the left and up on the right? The degree is odd, 5th degree. The term itself is positive, x to the 5th. So the end behavior says down on the left, up on the right. By the way, in your homework problems for, I believe it's 3.2, when they describe that, they say falls to the left, rises to the right, just so you know the vocabulary they're using. I just say down, up, you know, but they're a little more formal, I guess. Okay, what if I told you that this thing factors this way? By the way, notice that last one we looked at was 4th degree and it had 4 factors. This one's 5th degree and it turns out it has 5 factors, right? So what are the zeros of this function? -3, -1, and 2. Now, it's 5th degree, but there's only 3 different numbers that make it 0. Remember, there's supposed to be 5 numbers that make it 0. Well, there sort of are. It's just there are 3 different numbers that make it 0, but those 3 numbers between them make it 0 a total of 1, 2, 3, 4, 5 times. Y'all see that? So notice -3 makes this factor 0. Well, -3 also makes this factor 0. Y'all see that? So -3 shows up as a 0 2 separate times. Do y'all see that? I'm going to put a little M2 next to that. I'll explain what that means in a minute. Now, -1 only shows up as a 0 one time, right? Its factor only shows up one time. I'm going to put a little M1 next to it. 2 shows up as a 0, again, 2 different times. Y'all see that? The factor that makes it 0 shows up twice. And I'm going to put a little M2. So notice this little M number I'm putting out here is just how many times that number occurs as a 0, right? We have -3 makes that factor 0 and that factor 0. So -3 makes the function 0 sort of 2 different times. Y'all see what I'm saying? -1 makes this factor 0 and it only happens 1 time. +2 makes this factor 0 and it also makes this factor 0. So +2 sort of makes the function 0 2 different times. So that number where I put the M2, that means -3 shows up as a 0 2 times. -1 shows up as a 0 only 1 time. +2 shows up as a 0 2 times. Everybody see that? So that number is called the multiplicity of that 0. So the -3 has multiplicity 2. That means it shows up as a 0 2 times. -1 has multiplicity 1. That means it shows up as a 0 exactly 1 time. +2 has multiplicity 2. That means the number 2 shows up as a 0 2 times. Everybody see that? That multiplicity, the multiplicity of each 0 is important because here's what happens when I graph this thing. Now notice my y-intercept is 36, right? So I'm going to scale my y-axis and I'm just going to be cheesy. I'm just going to go by 9, 18, 27, 36. I'm going by 9s, okay? So 36 is my y-intercept. My zeros are -3, -1, and +2. And I know that the end behavior is, get up where you don't see that. My end behavior is down on the left and up on the right. And I've just got to figure out how to connect the dots. So when I come up and hit this 0 at -3, there's 2 possibilities. Either I pass right through the x-axis, in which case I would need to turn in time to hit that x-intercept, right? Or maybe I come up and hit that x-intercept, and instead of passing through the x-axis, maybe I just bounce off and kind of turn down again. Now, if I do, I've got to come up in time to hit that 0, right? So the question is, at this x-intercept, -3, does my graph pass through the x-axis or does it hit that x-intercept and turn? It's gonna hit this x-intercept and turn. That's what multiplicity tells you. If the multiplicity of that 0 is an even number, -3 occurs as a 0 an even number of times, 2 times, it's gonna bounce off. So if the multiplicity is 2 or 4 or 6 or 8, it's going to bounce off. If the multiplicity is odd, so notice -1 only occurs as a 0 1 time, and 1 is an odd number, right? If the multiplicity is odd, it's going to pass through the x-axis. So when I get to -1, I know I don't bounce off. I know I pass through. And of course, I got to hit that y-intercept, and somewhere up here I got to turn and come back down. So then I'm going to come back down and hit this x-intercept here at 2. When I hit that x-intercept, am I going to pass through the x-axis or am I going to turn and go back up? I'm going to turn and go back up because notice that 2 has even multiplicity. Its multiplicity is 2. So when I hit that one, I'm going to turn and go back up. And so that's what our graph would look like. It's down on the left, up on the right. It hits that x-intercept -3, turns, and then turns in time to come up and hit the x-intercept -1. But there, it passes through the x-axis, hits the y-intercept, turns, comes down and hits this x-intercept too, but because it has even multiplicity, it's 0 occurs exactly 2 times, an even number of times, it turns and finishes going up. Everybody see that? So the multiplicity thing is kind of important. All right, so now, I think we got everything we need to sketch a reasonable graph of this kind of thing, except we don't know how to find these x-intercepts, right? Like I say, the 2 that we've done, I cheated. I factored. What I really did is before class, I wrote this out and I got Wolfram to multiply it for me and tell me what that looked like. So I had already seen this factored. Otherwise, I would not have known how to factor that. Huh?
Can I use that on my?
No, but I'm going to show you what you can do instead. So we're going to learn to do something called synthetic division. And this first example is not geared to help us find x-intercepts. It's just geared to help you learn to do synthetic division. But synthetic division is the key to us being able to find those x-intercepts. So synthetic division, here's what's going on. And so y'all look at this. This is actually kind of, this looks kind of astounding. What we've got is we've got this polynomial function f of x, which is 2x to the 4th minus 3x to the 3rd plus x squared minus 3x plus 2. We want to, now this is not a number, right? It's a function. We want to divide this thing by x minus 2. X minus 2 is also not a number, it's a function. We are trying to divide a function by a function. And we want to actually do that division, just like how we divide 2 numbers. So how do we do it? That's the question. Well, one way to do it is with what's called long division, and it tries to mirror the long division that you learned in grade school to divide numbers. Sometimes you have to use long division, but for everything we're going to need, you can always use synthetic division. Let me tell you what you can and cannot do with synthetic division. You can divide any polynomial, like 2x to the 4th minus 3x to the 3rd plus x squared minus 3x plus 2, but you could divide any polynomial by any binomial that just looks like x plus or minus a number. So that's really about all you can do with synthetic division, but that's pretty amazing. You can divide this by anything that looks like x plus or minus a number. So in this case, we're trying to divide this entire thing by x minus 2. And y'all might be thinking about that now going, what does that even mean? I get it. I get it. If you've never done this, it's going to look kind of foreign. But I want you to watch me. There's a pattern to doing this. And the pattern is, it's elementary school simple. But you got to see what the pattern is. Once you see it, it's easy to do. So I'm going to try to write this the way the book does, although I don't like how they write it, but just for clarity's sake. All right, so I'm going to make this little sideways L looking thing, and I'm going to put some numbers in here. I'm going to put 2, -3, 1, -3, 2. Somebody tell me where I got those numbers from. They are the coefficients of this polynomial that's being divided. Do y'all see that? 2x to the 4th, -3 x to the 3rd, plus 1 x squared, minus 3x plus 2. 2, -3, 1, -3, and 2. Everybody see that? So that's what always goes here. All the coefficients of the polynomial that's being divided. Now out here, outside this little L, I'm going to write the number 2. Where did that number come from? Where did this number come from? It came from this binomial that is our divisor. Remember, the thing you're dividing by is called the divisor. Our divisor is x minus 2. And of course, the big function here that we're dividing, that's being divided, is called the dividend. So the coefficients of your dividend polynomial go inside this little sideways L. That's a good question. So the number on the outside here where I wrote 2 comes from our divisor x minus 2. Well, this isn't x plus 2, like this is positive 2, but that's a negative 2. Y'all see that? It's because whatever number you put here, y'all listen real close to this. The number that you put out here is whatever number you would plug into the divisor in place of x to make the divisor 0. See how that idea just keeps popping up all through algebra? So one way to think about it is whatever this is, reverse the sign of that constant term. And that's going to be what goes here, right? If this was x plus 2, I would put negative 2 out here. Everybody with me? Okay, so that's how we set it up. Now, I'm not going to explain what I'm doing this first time. I'm just going to do it. I'm not going to explain a thing, so don't freak out when you don't see what I'm doing. I just want to do this because we're going to do it really slow. I want you to see the reason synthetic division is super valuable. One of the two reasons is because once you know how to do it, it's super fast to do. Like you can do this division faster than you could divide, say, a 5-digit number by a 3-digit number by hand. So just let me do it and then I'll explain what I did. I'm finished. And I can tell you what the answer is. The answer is, it is 2x to the third plus x squared plus 3x plus 3 with a remainder of 8. Remember, sometimes when you divide things, you get a remainder. We did. We got a remainder of 8. That's the answer. How long did it take to do that? A couple of seconds, right? Now I'm going to show you what I did. And so let me come down here and draw it again so we can just start from scratch. So 2, negative 3, 1, negative 3, 2. So that's exactly what we had. These are the coefficients of our dividend polynomial, the thing being divided. And remember here I put positive 2 because if it's x minus 2, you always reverse that sign. That's because 2 is what you'd plug in place of x to make that divisor 0. So here's how you do it. Here's the pattern. I'm going to do it slow, and y'all watch close because you got to get this pattern pretty quick to figure out how to do this. So whatever your first number is, and I'm just going to call this our L. Whatever this first number is inside your L, you are going to bring that number down below the bar. Everybody see that? Always. Whatever the first number is, you bring it down below the bar. That's how you get started. Then here's what you do. You multiply 2 times 2. Everybody see? You multiply 2 times 2. 2 times whatever that number is you brought below the bar. That's equal to 4, right? You bring that 4 up diagonally under the next number, under the negative 3. Everybody see that? So y'all look, if you're looking down, look up. I did 2 times 2 is 4. I brought that 4 up diagonally under this next number. Everybody see that? Now I'm going to do signed addition. So that's negative 3 and positive 4. Negative 3 plus 4 is 1. That goes below the bar. Everybody see that? That's it. Now you just keep doing that till you finish. So what do I mean by that? Well, now that we got this 1 below the bar, now I need to do 2 times 1, which is 2, right? And I'm going to bring that up diagonally under the next number, under that 1. Everybody see? So again, I did 2 times 1, which is 2. I brought it up diagonally under the next number, which is 1. And I'm going to do signed addition. That's positive 1 and positive 2. 1 plus 2 is 3. That's what goes below the bar. Now I'm going to do the same thing again. I'm going to do 2 times 3. It's always, whatever this number is on the outside, you always multiply it times whatever this number is that you just brought down below the bar. Everybody with me? So 2 times 3 is 6. You always bring that up diagonally under the next number. Everybody see? So, and then you always do signed addition. Now I've got negative 3 plus 6, which is positive 3. That goes below the bar. And then I do 2 times 3, which is 6. I bring that up diagonally under the next number. And I do signed addition. 2 plus 6 is 8. I've run out of stuff to do, right? I've gotten to the end. I put this little backwards L, kind of a piece of a box around the 8. There's a reason for that. Because, so once you do this, you've done the synthetic division. Now what you've got to do is figure out, what does this tell me about my answer? Because remember, I'm trying to divide these polynomials. So how does this give me my answer? Well, the last number, I always put that little kind of box around it. The last number is always your remainder, always. And then you start going toward the left. The next number to the left of that is the constant term. The next number to the left of that is the coefficient of the first degree x term. The next number to the left of that, which is 1, is the coefficient of the x squared term. The next number to the left of that, which is 2, that is the coefficient of the x to the third degree term. And of course, if there were more numbers out here, you would then come to the coefficient of the x to the fourth term and the x to the fifth term and so on. So what have I got here in my answer? Well, I've got 2x. These are all positive, notice. So I have 2x to the third plus 1x squared plus 3x plus 3, our constant term, with a remainder of 8. Everybody see that? So so here's what I'm claiming then. I claim that 2x to the fourth minus 3x to the third plus x squared minus 3x plus 2 divided by x minus 2, I claim that that is equal to 2x to the third plus x squared plus 3x plus 3 with a remainder of 8. Like, what does that even mean? Well, think about what division means. So what if I did, let's think about if we divided two numbers. What if I did 14 divided by 3? Do you agree that I would get 4 with a remainder of 2? If I did 14 divided by 3, I would get 4 with a remainder of 2. Everybody see that? Because, you know, if I did the long division, 14 divided by 3, well, 3 goes into 14 4 times. 4 times 3 is 12. 14 minus 12 is 2. That's my, remember, 4 is my quotient, and 2 is my remainder. So what I'm claiming here is, oh, and by the way, here's what I actually wanted to show you. So when we say that 14 divided by 3 is 4 with a remainder of 2, how do we check our work to see if we, A, have done a division problem, and B, if we've done it correctly? Well, wouldn't we multiply our divisor 3, the thing we're dividing by 3, times our quotient 4, then we would add our remainder to see if we get the original dividend, the number was being divided. So to prove that I've done division and done it correctly, I would multiply my divisor 3 times my quotient 4, and then I would add my remainder 2. And if I've done a division problem here, and if I've got the correct answer, I should get 14, the thing that was being divided. And of course I will, right? So the point I'm making is, when we did this problem, and we're going to look at a couple more examples of this synthetic division. So if you're not sure you got the hang of that pattern yet, we're going to look at a few more examples. But what I'm claiming is when I did this division problem, this is the answer I got. And if that turns out to be true, if we can prove that we've done division and this is the correct answer, you saw how quickly I did that when I wasn't taking time to give an explanation. It's super fast. And it seems like that would be a lot harder than dividing like fairly big numbers, but it turns out it's way faster. At any rate, let's see if we can show that we've really done a division problem. Thinking about what we know about division, if this is the correct answer, if I were to multiply my divisor, x minus 2, times my quotient, which I claim is that, 2x to the third plus x squared plus 3x plus 3. If I multiplied all that, and of course combine the like terms, and then I add my remainder, do you agree that if I've done a division problem and if this is the correct answer to that division problem, when I multiply the divisor x minus 2 times that quotient and add that remainder of 8, this is what I should get. Do y'all agree? That's what division is. So let's see, and I'm going to run through this quickly. I'm just distributing. Y'all look, because I'm just going to give you a synopsis of what I'm going to do, and then I'm just going to zip through and do it. I'm going to multiply x times each of the 4 terms over here. I'm going to distribute it. Then I'm going to shift over to this -2, and I'm going to multiply it times each of these 4 terms. Then I'm going to combine any like terms, and I got to remember not to forget to add that 8 in to whatever the constant term is at the end. Okay, so here we go. X times 2x to the third is 2x to the fourth. X times x squared is x to the third. X times 3x is positive 3x squared. X times positive 3 is positive 3x. Now I'm going to move over to this -2 and I'm going to distribute it. So -2 times 2x to the third is -4x to the third. -2 times x squared is -2x squared. -2 times 3x is -6x. -2 times positive 3 is -6. And don't forget, we've got that plus 8 out there as well, right? So look, I could have just multiplied that all in one long line. All I did is I just kind of tried to line up my like terms. So now let's see what the answer is. We get 2x to the fourth, x to the third, 1x to the third minus 4x to the third is minus 3x to the third. 3x squared minus 2x squared is just positive 1x squared, which is just plus x squared. 3x minus 6x is negative 3x. And -6 plus 8 is positive 2. And isn't that what we started with? So we've really done a division problem, and we've done it correctly. So let's look at another example. So we want to divide this. This is similar to what we had a minute ago. This time we're going to divide it by x plus 3, okay? And I'll try to go pretty slow on this next 1 or 2, just to try to kind of get you, make sure everybody sees what we're doing. So, okay, we're going to put the coefficients of f of x inside here. Look, we got 2, -5, -11, 20, and 12. Everybody see? So 2, -5, -11, positive 20, and positive 12. What's the number that I need to write on the outside? -3, right? We're dividing by x plus 3. Then we need to put -3 out here, right? Okay, so first thing we do, we bring our first number, which is 2, below the bar. And now we're going to repeat these same steps over and over again. I'm not going to draw these arrows because they get too clunky. I'm going to multiply -3 times 2. Does everybody agree that's -6? I'm going to put that -6 up here diagonally under the next number, under that -5. Everybody see? I'm going to do addition. -5 plus -6 is -11. And that goes below the bar. Everybody with me? Okay. Now we're going again. Do y'all see this time? I'm going to multiply -3 times -11. That is positive 33. I need to move that up under my next number. I'm going to move -3 times -11 is positive 33. I need to put that under that -11 up here. Everybody see? -11 plus 33 is 22. That goes below the bar. Now I need to multiply -3 times 22. That is -66, right? -3 times positive 22 is -66. That needs to go diagonally under this next number. So now I've got 20 minus 66, and that is -46, right? That has to go below the bar. Now I've got to multiply -3 times -46, which is what? Positive 138, is that right? -3 times -46, I believe, is positive 138. That number needs to go up under our next number, under the 12. And then I'm going to add those numbers. And remember, whatever I get when I add these numbers is my remainder. And so is that going to be 150? Is that right? 12 plus 138 is 150. Everybody see? So you can see that, okay, well, these numbers might start getting sort of big, and you might have to, if you're not awesome at arithmetic, you might have to whip out your calculator or whatever, but the process is simple, right? Okay, now, before we do any more synthetic division, I want us to do something. So y'all look what I'm boxing in here. Here's our function f of x. I want you to find f of -3. In other words, plug -3 into this function in place of x. Tell me what you get for your answer. You can use your calculator if you want, whatever you need to do. So plug -3 into this function in place of x and figure out what f of -3 is. I feel like I haven't been giving y'all enough time to practice stuff, so here's a good chance for you to do it. Like I say, practice with your calculator if you need to, however you need to do it. And when you get an answer, tell me what your answer is. Y'all either didn't bring your calculator, you're very slow with your calculator, or you're just hard-headed and you're determined to figure it out by hand. How many of you are just determined to figure it out by hand? Okay, nobody. Okay, everybody at least brought a phone. Okay, then I can just surmise that y'all are all really slow on your calculator. Well, maybe just with your calculator. Anybody got an answer? I'm going to do this on my calculator because I want y'all to see why this should be way faster than it is. Let me turn that little light off. Let me zoom in. So look, we've got 2 times negative 3 to the 4th minus 5 times negative 3 to the 3rd minus 11 times negative 3 to the 2nd plus 20 times negative 3 plus 12, and then we hit our enter key. That shouldn't take very long, right? And it claims that the answer is, my calculator claims the answer is 150. Anybody get that? So I know I'm being real mean-spirited here, but I am trying to make the point that if you're taking college algebra, you ought to at least get comfortable using your calculator to plug numbers into something, right? At any rate, it looks like that when we plug negative 3 into this function in place of x, we get 150. Where else do you see that number 150 at? Oh, our remainder is 150. Do y'all see that? So is it just coincidence that when we put, remember we were dividing by x plus 3, which meant we put negative 3 outside here, right? Let's zoom back out. We put negative 3 outside here, and we did this synthetic division, and we got 150. That happens to be exactly f of that number, negative 3. In other words, the remainder you get when you do synthetic division is exactly the same as the answer you get. Y'all look where I'm pointing. If you plug this number into that function. Y'all see that? I know it seems weird. When I first saw this as a very young man, I thought it was some kind of weird black magic, and I was convinced that like math was demonic or something. Some of y'all are convinced of that today. It turns out that this always happens. So the fact that it always happens is called the remainder theorem. So what it tells us is there's more than one way to evaluate a function. One way to figure out what you get if you plug negative 3 into this function is to literally plug negative 3 into the function and then just calculate it and see what it's equal to. Clearly that wasn't working great for y'all because y'all were taking a really long time to do that. The other way to do it is to do synthetic division on this function using this number, negative 3 on the outside, and whatever your remainder theorem is, that's the same as the answer you'll get if you plug negative 3 into the function, and that's super fast to do. Y'all see what I'm saying? So this remainder theorem thing's kind of important, and there's another reason it's important. And let me show you, we're going to do that. So we're going to use this same function again. So let me write it again. I hate having to write this over and over, but you know, you can't erase a Sharpie, so okay, what if we did this synthetic division on this thing, but what if instead of putting negative 3 out there, what if we put positive 3? What if we put positive 3 out here? You know what I'm saying? So do you agree that if I were to put positive 3 out here, technically I would be dividing this by x minus 3, right? Everybody with me? Okay, but I'm going to do that. So I'm going to put positive 3 out there. And so we got 2, negative 5, negative 11, 20, and 12. I'm going to go a little bit faster this time, and my advice is don't have your head down staring at your notes. Watch, because this, if you haven't got this figured out yet, this is a simple little algorithm. And I don't mean algorithm like YouTube telling you which videos to watch. An algorithm's a little sequence of steps that you repeat over and over again to accomplish a purpose. You always start, in this case, I'm going to bring this 2 down below the bar. And you multiply these numbers. 3 times 2 is 6. That goes up under the next number. Do addition. Negative 5 plus 6 is 1. Goes below the bar. You multiply. 3 times 1 is 3. That goes under the negative 11. Negative 11 plus 3 is negative 8. That goes below the bar. 3 times negative 8 is negative 24. That's going to go up under the next number. 20 minus 24 is negative 4. That goes below the bar. 3 times negative 4 is negative 12. That goes up here under the next number. And 12 minus 12 is 0. Okay. What's our remainder here? 0. When you do division and the remainder is 0, that means that that thing divides evenly into it, right? So like if you were to do, instead of 14 divided by 3, if you did 12 divided by 3, you would get 4 with a remainder of 0. And that literally just means that 3 times 4 is 12. There's no remainder to add. Remember when we put this 3 out here, we were really dividing by x minus 3, right? Right? And so we can say, we saw that this was really division, and this answer here is, let me find a piece of paper. This answer we've got is 2x to the third plus 1x squared. I could just put plus x squared minus 8x minus 4 with a remainder of 0. What that means is, remember what I was doing here was dividing this whole thing by, this is plus 3, so I was dividing it by x minus 3, right? And that means that if I were to multiply that divisor, x minus 3 times this quotient, my answer, which is 2x to the third plus x squared minus 8x minus 4, that is exactly equal to 2x to the fourth minus 5x to the third minus 11x squared plus 20x plus 12. Do y'all see that? Okay, so this is our original function. Do you see that 0 is going to make that entire function? I mean, 3 is going to make that entire function 0? Because if I plug 3 in for x, 3 minus 3 is 0. It doesn't matter what I get over here when I plug 3 in for x, because that's going to be 0 times this stuff, and that's going to make this whole thing 0. Then 3 is one of the zeros of that function. Do y'all see that? So here's our function f of x. If we're trying to find all its zeros, the x-intercepts for its graph, we just found one of them. Y'all see that? Okay, now imagine I could do this. See, I started out with this 4th degree thing. When I found one of the zeros, that gave me one of the factors, which means I've now begun to factor this as well. Do y'all see? Remember, we don't know how to factor this thing, but we've kind of started factoring it. Okay, so what if now I know what makes that factor 0? It's 3. I just found it here. What if I now try to find something that makes all of this 0? And so notice the coefficients here, 2, 1, negative 8, negative 4. 2, 1, negative 8, negative 4. 2, 1, negative 8, negative 4. What I'm going to do now is I'm going to do synthetic division on that thing, where this represents 2x to the third plus x squared minus 8x minus 4. Okay, there is no remainder, so that's it, right? Okay, what if I put, I don't really know what to put. Maybe, what if I try 2 out here? That means technically I'm dividing this thing by x minus 2, right? But what if I put 2 out here and I do the synthetic division? So go a little faster this time. The 2 goes below the bar. 2 times 2 is 4. That goes up under the next number. 1 plus 4 is 5. Goes below the bar. 2 times 5 is 10. That goes under the negative 8. Negative 8 plus 10 is 2. Goes below the bar. 2 times 2 is positive 4. Goes up under the next number. Negative 4 plus 4 is 0. Oh, well, 2 must also be one of the zeros of this function, right? And from a factoring standpoint, what I've got here, what I have down here now is, let's see if I can fold this. See what I'm doing. So remember, that's the remainder, 0. 2 is the constant term. 5 is the coefficient of the first degree x term. 2 is the coefficient of the second degree x term. So what I've got here is 2x squared plus 5x plus 2. That's my quotient. There is no remainder, which means that, remember, this means I was dividing by x minus 2. If I multiply x minus 2 times this quotient, I will get this thing that was 2x to the third plus x squared minus 8x minus 4. And if I multiply all of that times, remember when I did this synthetic division, that was really dividing by x minus 3. So if I multiply x minus 2 times all of this, that's going to give me that third degree thing that I had here. Well, that third degree thing that I had here, if I multiply all of that times x minus 3, that's going to give me this original function back. Do y'all see that? Well, guess what? We don't know how to factor this, but we're factoring it anyway. And we've already found 2 of the zeros. 3 is a 0, 2 is a 0. If you don't believe it, just plug 3 into this function. You'll see that you get 0. Plug 2 into this function in place of x, you'll see you get 0. I know that because the remainder theorem says that whatever I get for the remainder here, in this case 0, that's f of 3. Whatever I get for the remainder here, 0, that's what I get if I plug 2 into that function. So that is f of 2. And once I get here, so look, this is fourth degree. We would expect it to have 4 zeros, right? I found 2 of them. There are 2 left to go. I could keep doing synthetic division, but I don't want to do that. The reason is I don't need to. This is 2x squared plus 5x plus 2. That is second degree, and we already know how to solve a second degree equation equals 0, right? We could factor it. And if we couldn't factor it, we could use the quadratic formula. And that's why when you're finding zeros by doing synthetic division like this, notice what happens. It started out as fourth degree. And when we found our first 0, the thing we had here was third degree. And we found a 0 there. Now this thing is second degree, right? It goes down by 1 degree each time you find a 0. Once you get it to second degree, don't keep doing synthetic division. And there's a reason for that. We'll take it up more on Wednesday night because we're just about out of time tonight. But the reason is this is only going to work if your 0 happens to be a rational number, either an integer like 3 or -5, fraction like 1/2 or 2/3. If it's an irrational number like we saw earlier, like 2 plus the square root of 3 or something like that, you won't find it. So what you're hoping is that all your that no more than 2 of your zeros are irrational or non-real. You're hoping that most of your zeros are rational numbers. This thing, I could just factor it, I think. And if I couldn't factor it, I could use the quadratic formula. But see, looks like if I did this, I think that would do it, because notice 2x times x is 2x squared, and when I do last times last, 1 times 2 is 2. When I do the outside and inside parts of FOIL, I'll get 4x plus 1x, which is my positive 5x in the middle. So the other values of x that make that 0, using our shortcut here, is -1/2, -1/2. And then -2 plus 2 is 0, so -2. So that function, it's got -2, -1/2, 2, and 3. 2 and 3, that's the ones we found with synthetic division. That's all the zeros. I know it is because it's fourth degree and I've got 4 separate zeros. And of course I could use that information if we had more time to sketch the graph and do a pretty quick sketch. It's going up on both ends because it's positive 2x to the 4th. Because each of these zeros has multiplicity 1. See, it's fourth degree and there are 4 different zeros, so they must all occur exactly one time. Every time the graph hits one of those x-intercepts, it's going to pass through the x-axis. So then here's the thing I have not told y'all yet, and hopefully we'll get to this Wednesday night, because I'm kind of rehashing Wednesday night what we did tonight. I'll try to show y'all different examples just so at least you get the value of having more different examples to look at. What I haven't told you is how I knew to try these numbers in the first place, right? So obviously what we're doing when we do this synthetic division is we're trying to put a number out here that's going to give us a remainder of 0. The problem is there's only 4 numbers in the universe that'll make that 0, and there's infinitely many numbers in the universe. So the odds of us just randomly picking a number here and it happens to make this 0 are pretty low, right? Like you might try 100 different numbers here and you might never get a remainder of 0. So what I haven't told you yet is how I knew what numbers to try. There's got to be a way to narrow down from all real, an infinite number of numbers to just a small handful of numbers that have a chance to make this 0. And so when we do this stuff on Wednesday night, we'll talk about how you do that. By the way, the stuff we're doing right here, the synthetic division, that's actually in 3.4 of the college algebra homework. Wouldn't expect you to do that yet. I'm just trying to show y'all the stuff that's coming up so you've seen it. Because again, on Wednesday night, like I'm going to have to be going really fast. We're just so out of time. So I just wanted y'all to see this, and I'll get this. Let me stop recording here. And I will try to get this posted in the next day or so. If you